This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so let's continue our discussion today with glass. Now, we've already spoke about glass when we saw the pre-modern glass industry. So this is a bit of a follow-up from that. That takes us to modern days, almost. And obviously, the topic is very large. There could be, many things that could be said. And so, in a brief span of less than an hour, I'd like to touch on glass manufacturing methods and how they have evolved after at the beginning of the 1900s. In particular, how we sort of transitioned from those fascinating methods of glass blowing that were used, for example, in the Crystal Palace, to systems that became more industrial in a true sense, so less reliant on craft and more on machinery. And then some key products that continue today, and just a few mention of understanding when they came in place and why, and potential problems that also derive from those first products. So there are some important failures in history in glass technology that it's worth in buildings and that it's worth going through. And finally, a case study, which is an example of technology transfer. How glass, in effect, was a very interesting field of movement of ideas and technologies between the automotive industry in particular and architecture and construction. So first of all, manufacturing. Now, manufacturing, it's the right term to use when we're speaking about modern glass, because in the past, although there was an element of pre-industrialization always involved in glass production, the reality was a lot of it depended on the skill and the art almost that was involved in producing glass by using a physical skill. In fact, it's not by coincidence. If crown glass, for example, was done by people, generally speaking, had to be tall, and you had to have certain characteristics, certain abilities that were not very common. But so the first point of transition is when we start to see how machinery starts being introduced in glass manufacturing processes to replicate more or less what humans tended to do by trade and by craft. So one of the first machines that were introduced was this one, which is what was introduced before this picture was taken, but it's a system that the Laba process that was basically creating an automatic blowing machine. So you can see here in the picture how you have a cylinder that is very much the same kind of product ultimate concept of the large cylinders that were blown and spun and to glaze the Crystal Palace, right? And yes, there was some equipment involved, if you recall. There wasn't just about handling these very large cylinders by hand. There was some machineries that the Chance brothers introduced to help the glass blowers. But here you have a machine that is using compressed air mechanically blown to reproduce a cylinder, which would then be you can see the cylinder sort of coming out of the furnace below there, and it's sort of glowing. So it's obviously hot glass here that it's expanding as a result of having blown air inside. And then the cylinder would be cut and it would be flattened and eventually annealed. But you can see some of the idea is just to use more or less what you used before. Other systems, again, took the idea of the plate glass, if you recall, that was introduced particularly in France. It was used also in Venice for mirror making, where the idea here is to cast glass over a flat plate, let it cool down, and then let basically gravity do its job to flatten the surface. After which, of course, the imperfection of the casting will be pronounced to have a flat surface. And so after this, normally the glass will be set up on these rotating tables where the glass panels would be grinded and polished using putting some plaster over them in order not to damage the glass, but they were subject to a very laborious process of polishing. That again, it's sort of semi-mechanical here, but it is still using more or less the same ideas of the old methods that were introduced in France in the 1600s. On the other hand, we see the developments of other systems that are more of a paradigm shift. And these are the precursors of the ways we make glass today, of which there were two broader families. There was a family that basically took the glass straight out of the melting tank using some sort of ceramic floats to induce the glass to become a ribbon. And then this glass was literally pulled up vertically through a series of rollers that would just progressively cool it down until it solidifies at the top of this tower. And then at the top, you can see the glass coming out of these rollers. In that process of that, so it's a very slow process where the glass is coming out. And while it's coming out, it's being annealed at the same time. Now, I will not go into this, what annealing is about, but so that you know, if you do not, once you prepare glass and you take it out of the furnace, as it is, the glass is very susceptible for breakage, even more than it is normally, much more. So it becomes virtually impossible to cut it along a straight line. There are residual stresses inside the glass after it's cast that need to be evened out. It's almost like if you have to season the glass after it's made for a period of time to redistribute, to eliminate as much as you can any of these potential irregularities inside the structure, in the molecular structure of glass. And so the annealing process is a process of warming up gradually to ease glass back into a position where it can withstand the normal environmental temperature. Now, normally annealing was always been part of the glass process. If you have cylinders, you have to do it in an annealing oven, so you have to do it separately somewhere else. But here the idea is to combine the annealing into the glass making process. And this is the Foucault method, which was developed, in Europe and in Belgium, that use this method where you stack in vertically your furnace, your glass shaping into a ribbon through some rollers, and then the annealing process. And once the glass comes out, it's already annealed, okay? There was also another method that was developed in the United States that instead of being vertical was horizontal. And this is very much the precursor of modern glass making, where you have, again, the assembly chain here, where you have a furnace, obviously the batch elements, sand and what other elements are added to it, soda and lime are all mixed together. They're fed into the furnace melts the glass, and then the glass is picked up in this time horizontally, not vertically, passed through a series of rollers, very long. And in that process also, it's taken through a layer, which anneals the glass, and the glass comes out flat. It's cut because it's annealed, you can cut it safely, and then it's distributed. And so this is the industrial methods of glassmaking. Needless to say, this is also the point where glass craft is completely expelled from the glass process. Glass become a matter of industrial production. It's one of the leading industry in machinery making. It's firmly intertwined also with the growth of the automotive industry, as well as in the aeronautical industry, any transport industry, for obvious reasons, because you need to look out of vehicles so that the vehicles can be operated and be safe. But it's also intertwined with, of course, with the construction industry, where glass become available in large quantities, in larger quantities than were in the past. It becomes less of a luxury product, and it's also available for windows and shop fronts and facades. Now, until the 1940s and 1950s, really, these methods of glass were the dominant one. So you had glass that was produced with these industrial mechanisms, they annealed glass, but they ultimately had a glass that once it was out of the factory was not still ready all the time to be used in practice. For some application it was, but for any application that required perfect visibility through the glass, so without having any optical distortions through the glass, there was another process that was involved, and that was the famous process of polishing, and that led to plate glass. So when we're speaking about plate glass, which was the dominant material, I'd say until probably the 60s and some the 70s up to a point, but plate glass was a product that was produced industrially, but it was polished also industrially. Why polished? It wasn't essential to be polished so you could see through. So if you had a window that you wanted to look out through it clearly without having any optical distortion, it had to be plate glass. And so there was an additional process of grinding and polishing. Yes, it was mechanical, but it was still fairly expensive. That made plate glass a product that was dearer than ordinary glass, that had this kind of, yes, you could see through, but you had a wavy kind of outlook through it because of the distortions that were induced by these sequences of rollers for which glass was put through out of the furnace and also through the annealing layer. So very expensive methods of polishing were developed. The first ones involved having mechanical machines in these very long arrays in factories that gradually removed an imperfection from the surface of the glass, reducing it to a perfectly smooth finish on one side, after which the glass panels had to be flipped over and finished off on the other side. Some manufacturers developed, like Pilkington and Ford being the same Ford of the cars, and that started to get involved in glass production because the automotive industry was growing so much faster than the glass industry could provide. So Ford themselves, they become actually producers of glass for their cars. And with Pilkington, they developed these mechanisms that are, of course, an evolution of the assembly chain for which Ford was famous for, that minimized also the amount of polishing by having twin grinding. So you can see here, there's a very fine line there. That is actually a sheet of glass that is coming through two rollers that are polishing the glass simultaneously on both sides. So you're halving the period of manufacturing that's involved in providing plate glass. And what we're talking about here is a global industry. I mentioned Pilkington, I said Ford was involved, but there's other dominant players like Libby Owens Ford was the company that developed the horizontal drawing method of plate glass. I've illustrated before. We have PPG, Pittsburgh Plate Glass Company in Pennsylvania. And we have also Belgian glass makers like Glaverbel that become very important. So a global industry of glass starts to Saint-Gobain in France, another very important player. You can see how some of the older centers, UK, Belgium and France somehow continue. But of course, then the United States of America become an important contributor to this global supply of glass. Why? Because you need to have a very high energy resources involved. So glass requires an enormous amount of energy to be used. So it's not by coincidence, like in the past, of course, forests were the resource, and fortunately, that's not the case anymore, but gas becomes the fundamental, the availability of natural gas in order to melt glass at very high temperatures becomes the essential resource to have plants of glass. So for that reason, some parts of the United States become big producers of glass. And then from there, the glass industry expands worldwide. Japan, and eventually today you'll find that China, of course, has a very big share of that glass production. All this up to a point where we have to stop, which is the float glass introduction. Now, float glass is something that in itself would be worth looking at as an historical achievement, but float glass is the glass that we use today. And float glass was invented as a system in the 1950s by Pilkington. Alistair Pilkington, being an employee of the company by the name Pilkington for odd reasons, someone with the same exact name, but Alistair Pilkington was one of the researchers and the inventors who came up with this idea of having glass rolled out, yes, in a horizontal fashion, but Pilkington developed a methodology of glass making that eliminated the need for the very expensive polishing that we saw before. So what Pilkington came up with, which was something that was sort of floating in the air as an idea, also by other manufacturers, but the brilliancy of this was that after the furnace, once the glass is molten, and you instead of taking it straight into the annealing air when it's soft and it's taken through rollers that would inevitably leave some undulations and imperfection on the surface, the glass is taken through a bath of tin. So it's floating, that's the name, float glass, on a molten metal tin that allows basically the glass to flatten itself perfectly, slowly and gradually, so that once it comes out of the tin bath and it's in a semi-solid state, the glass is strong enough to be taken through the rollers without having any residual marks from the rollers that will create a wavy surface. So in the traditional methods of glass production, you had glass that had a profile more or less like this, where by going through rollers, it became wavy. And so in order to become plate glass that was clear and you could see through, these waves had to be removed by the grinding process. In the float system, you have glass that it just comes out solid or almost entirely solid, that has two faces that are perfectly parallel. So no more grinding involved anymore. So glass becomes cheaper in a way and more available and more reliable. Now, before that happens though, and also while that happened, there's another front of innovation. So this is the methods of manufacturing by and large, but there's another thing that it's equally important, which is by understanding how products were made and for what purpose. And the purpose was very often, all the time, about performance. So glass is an interesting, a bit like the story of skyscrapers. Yes, they are a controversial part of the way we interact with the built environment, but they're also, things you should know about, because they are the efficient methods of production in themselves. They always strive to get the best outcome. So there's quite high rates of innovation involved. Now, glass as well is an example where the problems of performance become much apparent. Now, glass often looks like the same, but the products involved were not, and there were very significant differences that derive in part from the manufacturing processes that we described, but they were also driven by the need to have fitness for purpose once put inside a building or inside a car. So this is an example of a product that we already mentioned, plate glass. Now, plate glass, you see the intent here is to look through, and this is an advertising from Glaverbell being a Belgian company, that's illustrating this. If I put a chalk line, which was one of the quality assurance methods at that time, if I put a line through that, you can see me through. I don't see any distortion of that line. This is perfectly flat glass. And plate glass was the product that was used in many buildings worldwide up until the 60s and 70s, until float glass became the dominant material. And how was it used? Well, it was used for its optical qualities that we described, that give this beautiful, flat, polished look. But it was also used with tints to mitigate the problems of heat gain. And so we see a generation of buildings. This is the Shell Corner here in Melbourne. That building, unfortunately, was demolished. By the way, this building was designed by Skidmore, Owens, Merrill in collaboration with Buchan and Buchan. So SOM, the same architects we described and we spoke about when we spoke about skyscrapers earlier. In this case, was the San Francisco office of SOM in collaboration with a local architect, Buchan. And here it's one of the first buildings that uses plate glass to a great extent. And it's using plate glass of a solar grade type. So it's an American glass from PPG, from Pittsburgh, that is using this tint to mitigate the heat gain that is induced. So what was that? This was the way to somehow reduce the problem of having too much glare inside an office or having too much heat coming through in summertime, a big problem in Australia, but also to having heat leaking out in winter time, a bigger problem in the United States, for example. So heat absorbing glass was the product that really became important and dominant in this in Australia and in Europe during the post-war period, because it worked on this principle that because of its tint, it was able to absorb some of the heat from the sun and then emit that back inside or outside to a certain degree. It was not reflecting the sun away, it was storing some of the energy in its thickness in virtue of its color. And so you find why very often buildings of the post-war period often have a bluish tinge. Think about the Lever House or ICI House in Melbourne. And they're very similar. They are similar because that was the approach. If you tinted it in order to minimize the environmental impact inside the building. Or you had dark bronze, which is a darkish brownish gray color. That was also very common. Simultaneously with this, it was realized that, well, only one pane of glass doesn't do a lot, right? So, and it was understood from the 1930s that actually if you put two panes of glass together and you have an air pocket in between, you can actually have much better outcome from a thermal performance. And so double glazing was introduced in the 30s already in the glass industry with a very clear understanding of thermal implications, okay? Energy was a concern also in those days because bills were high, because air conditioning was expensive to run, not necessarily because of the same pressures we have today. And so double glazing evolved with a lot of trial and error. The two main products that were introduced were these two, one from PPG on the right and the one from LOF, Libby Owensford on the left. Thermopane being LOS product and Twindo being the one from PPG. Now, there were precursors of a current double glazing that were quite prone to failure. When you have two panes of glass and you have air being in between, the chances of having condensation, the chances of having some problems of leakage of air or air from outside into the chamber or vice versa were quite high. So these were not very reliable double glazing units. However, they were used very promptly by modern buildings in the post-war period. This being probably the very first they used it to a large extent. It's a building in Portland, Oregon, designed by Pietro Belluschi, an architect of Italian origin operating in the United States. And this was a building that it was a classic slab of post-war period that actually had a very clever use of double glazing. These are Twindos products by PPG. Double glazing was also used here in the inland steel, another classic example of modernist international style that it's often dictated as a generation of buildings that had no consideration for thermal performance, but it's actually far from the truth. The reality is that these buildings were not green buildings by all means, I'm not saying that, but they were actually very concerned about thermal performance. And they were, because there was running costs that were really significant, because the thermal implications were the most obvious. They actually tried to experiment and use these products, even if they were prone to failure. In these two cases, both glass being provided by PPG, actually the double glaze units continued to stay in place and they did not fail. And they were also used, this case instead, the LOS thermopane products were used in another building at the same time. This is contemporary to Pietro Belluschi's slab in Oregon, but it's a more traditionally looking building in Boston, where you can actually see how there's the concern here of saving, of minimizing the amount of energy inside the building, where For example, rather than having a curtain wall expanse, there's punch windows, and the solid walls. There's not a lot of windows around. There's an air conditioning system that's been implemented here, skeleton structure, and double glazing. Double glazing in 1948. Okay. Now, not all buildings were double glazed though, and for the greater part, up until the 1980s, very often towers continued to be single glazed. And one of the things that really came into play that probably in effect stopped the introduction of double glazing was the introduction of reflective glass. Now, reflective glass was, as the name implies, it still is used today. It's a glass system that has a coating, normally put at the back of the glass, that can be more or less mirroring in its effect. These being some examples that are extremely mirror-like. And reflective glass reflects back energy outside into the environment. So reflective glass became a synonymous of postmodern also glassmaking, but it certainly had an enormous benefit that allowed single glazed to be somehow to continue to coexist and being used. Reflective glass today is always used, but it's also used in combination with double glazing, which is a much better solution. But again, here what the idea was to increase performance, reduce the bills, particularly for the owners in this case, not necessarily without a lot of concern about the implications of these buildings and reflecting also on their surroundings, which didn't resolve the problem. But you can see here again how the glass industry is targeting this problem of glass and performance, and as a fundamental message also for advertising. This is an example here in Melbourne where you have glass from LOF, very trend, being a product from LOF, that it's reflective glass, and it's used here in the States House, next door to BHP House. The building is still stands up, by the way. Nice building by Young and Freeman. But reflective glass becomes the material that somehow prolongs the life of the glass box even into the 1970s and in the 1980s, which is probably arguably the real golden age of the glass box. Okay, Rialto in Melbourne is probably an example of the ultimate glass boxes of the 1980s, and it was when it came out in Melbourne, it was not only the tallest building, but it was also a significant addition to the skyline. That, in virtue of its reflective quality, I recall myself even moving to Melbourne in the early 2000s when Rialto still stood up a lot more than it does today. And the reflective quality of the building really played a lot of tricks, particularly in the sunset, and that they were quite of a landmark, I suppose, for the city. Notwithstanding all the controversy of the project, they still stand. And I'm quoting here from an article from The Age of the 1980s, which is actually quite intriguing. And you can probably find it online too. It's an article from Keith Dustin, who provocatively he said, well, as a good old greenie, initially I was actually against the Rialto, but now that I look at it, I'm actually converted. There's a bit of sarcasm in that, but the point is that reflective glass actually in glass buildings, they're not necessarily a product of the post-World War II period. They actually are very much, in my mind, and I argue, very much a postmodern product. So that carries on today. So we should, if you are probably prepared to question why we still do glass buildings today, I think it's not about blaming Mies van der Rohe for it, but I think we probably have to look more carefully about what happened in the post-war period. And this is some examples again that demonstrate the appeal of reflective glass towers, particularly in the 1980s, when you have this very clear advertising from Pilkington, beautiful and energy conscious, right? Believe it or not. So now, why this is important as well, because it provides a bit of a critical background to which we understand contemporary architecture. That it's a bit more factual than based on cliches sometimes, but modern versus postmodern, and I believe also it's important because it gives us an opportunity to understand from some failures, and some of the failures are widespread, I suppose, but some of the failures were also driven by specific projects, and some of these failures also pertain to Australia as much as to other environments. So there's a bit of a story about glass failures that it's important, especially here in Melbourne. And this story has global repercussions. As we saw also, Melbourne, it's an interesting test bed for high-rise construction in many regards. We even saw, someone like Fazlul Khan having an impact here in this city. And there's another little story that I want to tell, which is about the failures of glass that affected an important landmark, which is the ICI house. And before talking about that epic failure, there is a precedent. And the precedent is this building in Dandenong, the General Motors factory, where the architects specified, Stevenson and Turner, specified a glass that I can only see here in this picture, that was colored, spandrel glass on a solid wall, and it was Australian glass, that for some reason that at the time was not clear initially. The glass, colored glass, started to break and fall from the curtain wall. And so what happened is that they, instead of starting the blame storming that you would normally do today, it's not my fault, it's your fault, and I'll take you to court. Actually, the architects, the client, decided to understand, why is this happening? This is quite strange. The glass shouldn't break. The glass manufacturer didn't know why. And so what they did, actually, they engaged the CSIRO, the Commonwealth Research Institute, and they found out a material expert, Ballantyne, Ron Ballantyne, who was committed and took the task to understand why that glass broke. So what Ballantyne did, he went to the United States of America, informed himself, started to talk to other experts in the field, and he came back to Melbourne and explained the process. And look, what you witnessed there is one case of thermal breakage. So what it is that the glass is subject to thermal variations that are extreme. It's glazed in contact with frame that probably could have been done better. And because of this thermal variation, just a small imperfection on the glass is sufficient to open up a crack and the glass can fall. If you have just regularly annealed glass, like the head here, glass is not that strong and glass will fall. Therefore, the recommended option is that you use toughened glass. Now, toughened glass, you should know, it's a tougher type of glass or tempered glass that is stronger. So if you use glass that is stronger, being made stronger by a process called toughening that I'm not going to describe here. If you have glass that is stronger and tougher, then you are less likely to have thermal breakage, okay? So this then became the message that percolated to the industry. If you have glass spandrels and they're colored, and it could be colored because of a tinted sort of approach that I described earlier, heat absorbing, so you're absorbing heat, you see, in the glass. Well, if you use spandrels, you might want to use tougher glass instead of using, for example, annealed glass, regular glass. So many buildings were built in Melbourne after World War II that had curtain walls. Not too many really, but some of them still stand. And one of the most important one, most notorious one, was this one, the ICI house, which you can see here under construction, where the curtain wall has been installed using scaffolds, using people upsailing. And ICI house still today, you will recognize that as a blank wall on the western side of the building, that it's blue, like the rest of the building, blue spandrels, right? And ICI house, the architects at that time, being aware most likely of the advice provided by the experience gathered from the Dandenong problem, they specified toughened glass as industry would determine it would be appropriate to do. But what happened after that is quite interesting, because despite the fact that toughened glass we use, a lot of glass panels, 70 panels actually, to be exact, in a short span of a year, started to fall from the facade, from the western facade in particular, to the point that the contractor had to install a gantry, you can see it there, in place to protect pedestrians. Because obviously, these large panels falling from the facade down the street would become quite dangerous. And so, again, there was a problem. The problem was, well, why do we use toughened glass? Why it can't be thermal breakage, right? Or is it? And so again, what happened there? Went back to CSRO, same scientist, Ron Ballantyne, and Ron Ballantyne investigated the problem, and he came up with this explanation that was quite striking. He actually understood a problem, and the problem was Ballantyne being a scientist and an expert of chemistry more than anything else. He explained that the problem was not induced by thermal breakage this time, like in the Dandenong office, but it was due to the fact that toughened glass in itself has a very specific problem, which is nickel sulfide inclusions. Now, nickel sulfide inclusion are very small particles that are always present in glass. They happen during the glass melting process. But in the toughened glass in particular, because the glass is sort of put into a process of heating and cooling, these particles during the toughening process can expand themselves. First of all, they shrink themselves, they change state, and then once the glass is put back into the environment, in time, they have a risk to revert back to their initial state and expand. Now, toughened glass is that kind of glass that if you break it, it breaks it into 1,000 small pieces. And so while it is strong, once you break through its core and strength, it explodes literally. So this phenomenon is particularly relevant and important for toughened glass. And why is this historical important? It's because it happened, the understanding of this very much happened here in Melbourne because of this building. And so this family of failures somehow were understood at this point in history, led probably, arguably, also to some changes in the production of tall buildings in Australia, certainly, but also worldwide. So you find after that first phase of experimentation with glass facades, suddenly, if you look at buildings of the 1960s, you see that there's a lot less curtain wall and a lot more precast used. This has been a classic example, the Royal Insurance building. Precast panels, even if they don't look like it, they are precast panels with double glazing inserted into it. And more remarkably, you have a glass manufacturing company, the Australian Consolidated Industry, ACI, that build their headquarters in Melbourne, and they don't build their headquarters with a curtain wall, but they actually build the facade using precast. Okay, so some of those failures of the early curtain walls were actually something that slowed down the adoption of the curtain wall. And then arguably later on, once you had the innovation of float glass, reflective glass, and more reliability on double glazing, that's when the glass boxes come back. Another important failure I want to mention is the John Hancock failure. John Hancock in Boston this time, not in Chicago, as we saw earlier. And this is a case of pushing the envelope a bit too much for the time. The John Hancock building in Boston was one very controversial building also for its siting next to an historical landmark. You can see here in the background, by the way, the old John Hancock Center. I mentioned before the double glazed tower that are introduced. And here you can see these two slabs side by side. And you can see a close-up of the facade where you can see that there are no spandrels apparently, although there are spandrels, but the spandrels are behind and they're not visible. They have a transom that runs behind the glass. And the glass itself is reflective glass. This is the early 70s. And it's double glazed. So it was a very adventurous, what is very innovative also approach. And the architects were trying to use the best possible product for the time. Now the building, you can see here also this picture of how the older John Hancock building double glazed sort of also double glazed sort of reflected into the skin of the new one, the bigger one. John Hancock being obviously an insurer, one of those corporate companies, they were eager to build more headquarters and bigger and better. And you can see here the curtain wall being installed, very striking sort of glass facade mirroring the context, and also having no visible spandrels on the outside. Now the building is notorious because at some point, particularly after a stormy event in the city, a lot of panels on the facade started to fall and break, and to creating great alarm in the city. Why did they break this time? It was not nickel sulfide inclusions like in the ICR. It was not thermal breakage, but in this case, it was a failure of the double glazed unit. I said to you before, there was some problems with double glazing where often they fogged up. There were some issues of insurance performance within the products themselves. But in this case, the failure was induced by the manufacturing process itself of the product, which was the thermal paint system that was used by LOF. And so in this case here, what they had is given the right size, the big size of the panels, and given also the reflective coating that was inserted into the double glazed unit, what happened was that generally these days, we tend to do a insulated glass unit in this way, where we have a spacer, and the spacer in between the two glass panels is insulated by having some double tape, basically, or some sealant that it's also adhesive, that it's a rubbery substance that allows some movement, some tolerance. The double glazed units that we used at the John Hancock in Boston instead had a lead spacer that was basically welded, soldered better, onto the reflective coating that was applied inside the double glazed unit. So in other words, there was a continuous, a rigid connection kind of thing between the spacer and the coating that allowed very little adjustment for movement induced by the wind or induced by temperature differences. And so in other words, it created a weak spot along the spacer that could create cracking and failures. And so fundamentally, this was a manufacturing failure. Incidentally, also, the thing is sort of leaked throughout the industry, because for years there was a deal and a settlement case that was arranged between the manufacturer and the owner of the building. So the manufacturer rectified the problem, but the thing was hushed. It was taken to court, and the settlement made it such that it became confidential for a period of time. And it still is, to the extent that you will not find easily records of that. But nonetheless, the industry understood the problem. And here's an example of what the failure induced that particular problem. There was also a combination of structural issues here because of the wind. And there was a notorious, slogan that was introduced at that time when this tower lost so many glass panels that plywood had to be introduced as a temporary panel. Some local newspapers said, this was a case of ply in the sky, right? So now the glass failures are fascinating because even if there are some landmark histories, they keep coming back. Recently in Melbourne, you would know there's been some issues of glass balustrade exploding on the street. And personally, I was involved in some publications or media coverage because I found it ridiculous that some reporters were basically dictating the problem of faulty glass coming from China, probably misled by other problems that affected the industry. The reality is that some of the failures we've seen recently in glass exploding in Melbourne are simply from the fact that some specifiers, builders, or I don't know exactly, depending on the project circumstances, but somebody has forgotten the fact that toughened glass explodes because of the same reasons that it exploded in ICI House, except that in ICI House it exploded and people could not prevent that because they were not aware of the problem, whereas now today we are. And glass failures have been up until the late 90s. For example, here in this project in London, the terminal of Waterloo Station, where this very striking structure designed by Grimshaw somehow had a problem of nickel sulfide inclusion that failed because the toughened glass was used again in overhead in a very large station. Now, to the designers at that time, the specifiers and the contractor at that time, their excuse was they were actually trying to use heat-soaked toughened glass, which was, again, a new development that became more available in the 90s, with the promise that heat soaking would have somehow eliminated the problem of nickel sulfide. But it turned out that heat soaking does, but it doesn't do it well enough to be safe with it. So it still remains today that you don't want to have toughened glass overhead, because it's inevitable that there is a risk that some of that glass may break. Now, to conclude this, I'd just like to highlight another opportunity, I suppose, to learn from glass, which is the fact that glass also has acted as a vehicle of technology transfer. Technology transfer between different industry in the 1900s, and arguably might continue to do so in the future. Glass, of course, it's an inevitable material. You must have it in many circumstances. It's a fairly unique material. So you can get some surrogates, but it's very difficult to replace it. And again, the impact here of the World War II, it's one of the drivers that induced technology transfer. During World War II, a lot of the glass manufacturers in America were converted to production of military fittings, equipment, and vehicles. The glass industry reoriented itself, for example, to the production of canopies for aircrafts, which this is one example, the nose canopy of the bomber, the B-29 bomber being produced by Libby Owens Ford. Now, aircrafts for aerodynamic purposes need to be curved. The benefit from curve. So this is the point as well where curved glass starts to become available, and because of the necessities induced by another industry. In an aircraft as well, you want to insulate from the cold temperatures from outside. So double glazing also becomes used extensively during World War II, and curving. After World War II, a lot of the production of canopies becomes an instrument to promote car windshields, like you can see here, and cars themselves that are rounded and streamlined to replicate these ideas that come from the aeronautical industry. And so glass manufacturers started to invest and promote also the use of curved glass to a great extent, particularly for cars. And they become involved in finding solutions that are fit for purpose for the car industry. Now, one of the biggest concerns at that time, besides the aerodynamics and the looks and then the idea of marketing cars along the lines of what was perceived to be the best product for those days, the other issue that becomes apparent is the issue of safety with glass. So this is a time where also it's understood that it's a good idea to have a seat belt, for example. And so a lot of people apparently used to die in those days, not so much, yes, because of the seatbelt, but because they used to be, as a result of the impact, used to hit the windshields with considerable consequences. So you can see, unfortunately, these very scary pictures where you can see those are the signs left by the impact of people hitting a windshield. So, of course, the seatbelt prevents that to happen. But another thing that was understood then is that the glass should not break into shards, because even if you are anchored by a seatbelt and the glass shatters and sends 1,000 stars towards you, even if you're on a seatbelt, you're going to suffer from that. And so even if you don't hit the windshield, you're going to be impacted in a very violent way. So this is the point where the glass industry starts to address this problem. Yes, curved, but have to be safe as well. It has to be safe because it has to be such that if there is an impact, the glass does not send projectiles inside the vehicle. And it has to be safe so if there is an impact, the glass does not come off the frame into which it's set. So it stays in place, it breaks, yes, but it does not send missiles inside, and it does not become loose to the point that it's just launched outside of the car. And so laminated glass becomes the solution to this problem. Now, laminated glass is a sandwich of glass panels that are kept together by vinyl interlayer. You can see here in this advertising picture. The vinyl itself is not translucent when it's installed in the first instance, but then with heat and pressure, the vinyl becomes clear, and it becomes like a glue that keeps together two glass panels. It gives absolute visibility and it gives safety as well. And it can be also bent. It can be introduced into curved windshields, of which you can see some examples here. So the glass industry becomes very much involved into this idea of providing safety and providing also performance in their product. And one aspect of this safety was the importance of connecting the glass to the body of the car in ways that had to be innovative. Traditionally, in a car, when you install a windshield, you just fixed it more or less like you do in a window. You put it in a rebate, you put a strip all around it, and put some mastic and fix it in place. You would understand that if the windshield is curved, it's actually very difficult to house precisely and safely a windshield in it. And so the automotive industry therefore developed these systems of gaskets that are rubber products that can be fed through the edges of windshields, and that can be used to snap and secure safely the glass inside the body of the car, which is curved itself. And you can see here an example of somebody illustrating these methods of installing gaskets along the curved edges of windshields, and then these would be inserted into the body of the car. Now, among a range of families of products that resolve this problem, there was one product in particular that was developed by General Motors, and this was the zipper gasket. Now, the zipper gasket is basically a strip of neoprene. Neoprene is rubber. Imagine, same material that more or less you have in your wetsuits, right? And neoprene is flexible, but it's also strong enough. If you put some pressure on it, it sort of returns that pressure by gripping on things. So what General Motors did here, they invented a system for glazing windshields that had a strip like this that fed into a flange of metal. You can see this very nice drawing here from a patent. And then it has one channel there, one groove that is let loose. And so the procedure here is that first you insert this gasket along the flange, then you insert the glass in it. You can see the glass here coming into the gasket. And then a third element is sort of zipped through it to put compression into the gasket. And then this compression sort of grips the glass and at the same time is gripping the frame. It's rubber. It does not, it absorbs movement and vibrations, and it's keeping glass safety in place. Why is this important? Well, it's important because this technology it's transferred back into curtain walls. Curtain walls of the 1950s, like in this case, the General Motors headquarters, not by accident, designed by Saarinen, a building that once they start building a curtain wall, they realize they start to have some problems, they start to have some failures. The frames of aluminum and glass are not coming together. It's not necessarily thermal breakage, but the sort of, teething problem with aluminum and glass starts to become a nuisance in the industry. And glass methods that are traditional, they involve putty, they're very open to failures, they require skilled laborers and so on. So in this particular project, General Motors, being the client, said, well, you know what, why don't we just install the curtain walls like we do in our windshields? And so they did. They pushed this product idea onto the architect. The architects worked with it. They developed it to become suitable for a curtain wall in this case. And they did exactly that. They finished the curtain wall by using these neoprene gaskets. You can see here their shape. They are used to house a panel, not only the glass, but also the spandrels of metal, and then the zipper that comes into place that sort of completes the project. This technique became used not only here from the General Motors, but also in other projects. This is another project in Houston that happened years later in 1960s, and you can see here clearly how the gasket is being used here to secure glass into aluminum frame. And it was even used in precast applications. So the zipper became the link between the precast, which is notoriously hard and rough. When in contact with glass, this neoprene sort of cushion that secures the glass in place becomes also a good link that prevents any contact between glass and concrete itself. And you can see this used here in an application where it's embedded in concrete precast units. They're lifted up on site. And you can see here with a rubber mallet how they're feeding the gasket into the concrete. And it was used extensively in this building, even before some of these examples I've just shown. In fact, straight after the General Motors example, it was used in a tall building, relatively tall building in Toledo, Ohio. By who? By the glass manufacturers, W11 Force, who designed their own headquarters in the city where they produce glass in Ohio, and they use it extensively. Also, being the suppliers of glass as they were of General Motors for their cars, they had a special deal with General Motors for years, and they decided to implement this time zipper to fit also with double glazed unit. Okay, so they try to use the best possible outcome for the best possible product in those days, which was a product borrowed very much from the automotive industry, was also providing a safe gasket that was able to grip safely these double glazed units that, as we said, were notoriously open to potential problems of leaks, etc. And the designers, in this case being again SOM, this time from New York, and the builders and the client developed this strategy where the entire building was glazed in this fashion. You can see that they're using some swing stages coming from the top. There's the building maintenance unit of the building using to support these cradles. And then workers here are fitting these rubber gaskets all throughout the aluminum frames. You can see them working on this platform here. And you can see a close up here, how they fit in this gasket. This is the dark gasket coming into the flange of the aluminum frame. You can still see them here, loose, still in the process of being secured on the frame and fed through. You might be familiar with this picture when you go on LMS. And then you can see here how the next stage is to lift up the glass using these pressure caps, double glazed units. You can see here there's a little dark line, which is the edge of the glass. The cranes at the top are the actual building maintenance unit that eventually will become the crane that is used for cleaning the glass later on. And so the glass panels are put through the cradle, they're hoisted in, and they are fed through these gutters, so through the gaskets. They're lowered, obviously, carefully into place. And then a zipper comes into place to secure the gasket and put pressure against the glass. And off you go. And you can continue to do the work, obviously, by jumping to the next floor or moving sideways, using the BMU to continue with the next series of panels. So in this way, the whole building was very much clad. You can see the steel structure being in place, and then you can start to see how the BMUs have been set up, and the glass is progressively installed very quickly using this very clever system, and that it's also a very clear evidence that yes, you can do technology transfer in between automotive and in the architectural and construction industry. And so I'll finish here